I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
This week, maths. Love it or loathe it, it's everywhere, from bees to aliens. So we'll be taking a closer look at the language of the universe.
Plus, how getting a good night's sleep can help with chronic pain. Are electronic personal assistants going to take over the world? And lava in space. I'm Tom Crawford.
I'm Georgia Mills, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First, back in September 2015, a new species of early human, Homo naledi, was announced to the world. The remains were found in the aptly named Cradle of Life area of South Africa in the Rising Star cave system, and they changed the way that we think about human evolution. Now, another cave has been discovered, and new analysis of the skeletons within has shed light on what Homo naledi looked like and where they fit into the timeline of evolution. I spoke to the lead researchers.
I'm Professor Lee Berger. I'm a research professor at the University of the Witwatersrand in Johannesburg, South Africa, and an explorer in residence at the National Geographic. We've discovered first a new chamber with more Homo naledi, about 100 meters from the original chamber. It's called the Lesedi chamber. And it's got multiple individuals in it, including a partial skeleton of Homo naledi, an adult male we've called Neo, which means gift, by the way. It's not after the Matrix character. We also have finally dated Homo naledi from the Dinaledi chamber, the fossils that we announced in September 2015. And contrary to what I think practically every scientist who had seen or studied the remains thought, these individuals are not millions of years old, as they probably should have been by their anatomy, but they are relatively young, between 200,000 and 300,000 years approximately. And that places them in the presence, potentially, of modern humans, who we believe are evolving in southern Africa at that time. And certainly we're seeing the first, what we used to think of as the first archaeological evidence of modern human behavior.
Homo naledi, is this sort of a primitive human species in some sense?
Yeah, exactly right. And I'm John Hawks. I'm a professor of anthropology at the University of Wisconsin-Madison and at Wits University in South Africa. When we look at Homo naledi, and we have a better skeletal record now of naledi than we do of any other fossil hominin other than Neanderthals and modern humans. So we know a lot about it. And it's human-like in some aspects. It's human-like in its hands and wrists in many ways, in its feet. It's human-like in body size, and it's got very small human-like teeth, which indicates something about its diet. But much of the rest of the skeleton is very primitive. It has a brain about a third the size of modern human brains. It has a very primitive early Homo-like skull, and parts of the trunk are very primitive also. So it has this mixture of characteristics. It's been very difficult for us to try to figure out exactly how it's connected to us, but it's clear that its origin, its branching from our evolution, has to be something like 2 million years ago. So that's where people were thinking it would be.
But you've now shown that it's much more recent than that.
Exactly right. That lineage may have originated 2 million years ago. Looks like it. But this population existed in the very recent past, 200, 300,000 years ago. So it shows that there was a lineage that lasted up to 2 million years that was in Africa, evolving at the same time that our ancestors and potentially other lineages of archaic humans are evolving. It's a very complicated scenario. And even 5 or 10 years ago, we would have said this is probably a very simple scenario. So this has really shocked us, and it shocked many in the field.
And you mentioned this was a new cave that you've discovered. So was this branching off from the old cave system?
The Rising Star system as a whole has up to 2 kilometers of passageways underground that we've got mapped. Now, our first discovery, the Dinaledi chamber, was not on the map. And it was a very difficult descent down into it. Very surprising that we found, bones laying on the surface. As we were excavating that, our exploration team said, I think I've seen something like this somewhere else. And the original two discoverers of the Dinaledi chamber, Steve Tucker and Rick Hunter, showed us the Lesedi chamber. And it also had skeletal material on the surface. It wasn't as obvious, and it had been missed before, but we began to explore that. We began to do very limited scale excavations in it, and it preserves some of the best Homo naledi remains.
What's also fascinating is that the Lesedi chamber, which, by the way, means chamber of light, actually is almost as difficult to get to as the Dinaledi chamber, the original chamber. It's not quite as difficult. The squeeze is only about 25 centimeters instead of a terrible 18 centimeters. And I can attest to the difficulty because I've been in it once and almost didn't get out of it. I was stuck for almost an hour before they had to pull me out. But it's clear that Homo naledi was choosing to go into these very similar, very difficult to access chambers, generally 30 meters or so underground. That is really remarkable to think the journey that they would have taken to get to these two places and why they would have done that.
That is my next question then. Why do we think they may have been going into these chambers?
We know that we find their bodies. And bodies of individuals of all ages. In the Dinaledi chamber, at least 15 individuals, newborns to old adults. In the Lesedi chamber, we have at least 3 individuals, 2 adults and 1 juvenile, potentially more. So we know they're leaving their bodies there. What we don't know is how they may have been using other parts of the cave system. We are now turning to investigate that by excavating probably nearer to the surface where we use, and also by looking systematically for other evidence of naledi behavior inside the cave. In particular, we're super interested in the possibility that there will be evidence of fire somewhere in the cave.
So we went to initially a great deal of effort to try and explain any other reason that Homo naledi might be using these chambers except for ritualized deliberate body disposal, which a lot of people just didn't like. Several scientists wrote a couple of articles, which we responded to, and saying, well, a small-brained hominid can't do it. But that's about the only argument there is against that idea, just not liking it, that, one of the things we see as precious has been intruded on by, a hominid with a brain the size of an orange. The second chamber, finding a second chamber, the Lesedi chamber, that is practically identical in its formation, its location, its position, and contents to the first chamber, I personally think adds quite a lot of evidence to the idea that Homo naledi really was ritually disposing of its dead.
Professor Lee Berger and before him Professor John Hawkes discussing their work published this week in eLife.
Now back in the land of the living, we all feel the benefits of a decent night's sleep, but could not getting enough kip be making life literally more painful? New research from a team at Boston Children's Hospital and Beth Israel Deaconess Medical Center has shed light on the link between lack of sleep and sensitivity to pain. But what might this mean for the millions of people in the UK and around the world who suffer from chronic pain? Surprisingly, it seems a good old cup of coffee might help. Katie Haler spoke to pain scientist and study co-author Albin Latre-Mollier.
We wanted to understand the possible relationship between lack of sleep and pain sensitivity. To measure that using human subjects is extremely complicated. So we used animal models for which we have very little genetic variation and we can control the environment. And that way we could precisely assess both their sleep-wake patterns and their pain sensitivity. And we then exposed those animals to different sleep disturbances chronically to see how much it affected their pain levels.
So this is the equivalent of a human having a late night, maybe going out a bit too much or watching too much telly, something like that.
That was the goal we had in mind. The mouse would make the same mistake we're doing.
Presumably mice don't watch box sets. How do you entertain a mouse?
It turns out that mice love chewing, and I guess it comes with the fact they're rodent, and actually that makes them happy. Another thing we found mice love is cotton. And so we tried to come up with strategies where the mice would have to be curious and chew on some material to reach some nice cotton ball inside. And that would motivate them to stay awake. They can spend 30 minutes just having fun with them. So it was actually very cute to watch.
So just at the point at which they're wanting to go to sleep, you're going, hey, play with this cool thing. And that's the way that you chronically deprive them of sleep.
Exactly.
And you want to see if there is a link between how sleepy they are and their pain threshold. So how did you test pain sensitivity?
The standard one we used is exposing a mouse to a surface that is rather hot. And then we will measure the time before they go away. The more sleepy a mouse is, the sooner they're going to try and escape from a noxious stimulus. So they basically don't tolerate pain nearly as much as when they're fully alert. And interestingly, that's specific to pain, because if you expose them to other stimuli that are not painful, we observe either nothing, or the mice, because they get sleepy, they react less.
Do we know that this pain is caused by lack of sleep? Can we say that it's more than a correlation?
If it's a correlation, it's a very tight one, and it's very specific. So it doesn't prove the causality, but it strongly suggests a causality.
I mean, when I'm in pain, I tend to take a painkiller. Did you give them painkillers? What happened there?
Yes, we tried to give them probably the same painkiller you take when you're in pain, and to our surprise, that just didn't do anything. And then we also tried morphine, and we found that morphine's efficacy was strongly reduced in sleep-deprived animals. The only drugs that we found that could prevent and reverse temporarily this increased pain due to sleep loss were caffeine and modafinil. There are two distinct drugs that do not work on the same receptors, but they both promote wakefulness. And we found that these drugs were capable of restoring normal pain sensitivity in mice. Both are indirectly increasing dopamine levels in the brain. And some studies have recently shown that dopamine disruption can increase pain sensitivity and pain perception. When you don't get enough sleep, you might disrupt your dopamine transmission, and that could increase your pain sensitivity. I should add, though, it's very important that they didn't erase the sleep debt. So they're a good transient solution, but your lack of sleep is still there. You cannot replace your sleep by caffeine.
What does this mean for humans?
What we found is that the type of pain you can feel when you're not getting enough sleep is different from another source, inflammatory pain, or if you cut yourself. Those are different types of pain, and they can accumulate. So for people who have chronic pain, it's likely that the pain itself is going to prevent them from getting good sleep. And the bad news is that this lack of sleep is going to cause some new pain, and they're going to become even more sensitive to pain. And their treatments are either not working against this new type of pain, or are going to actually lose some of their efficacy overall. So treating the pain is one thing, but maybe to also try to help them get back their sleep. And that could help break this vicious circle and help them reduce some of the pain, and also then being more responsive to their regular painkillers.
Alban La Tremollia there, speaking to Katie Haler, and that work was published in Nature Medicine. You're listening to The Naked Scientist with me, Georgia Mills, and with Tom Crawford. Still to come, do cats really like milk? And can we use maths to make super effective ads?
But first, electronic personal assistants. These little voices are eager to assist in most smartphones, but now they are appearing in our homes too, in items such as speakers and lamps. There was even a recent announcement of a partnership with a car manufacturer. So the big question is, will we spend all of our time talking to gadgets? Tech expert and angel investor Peter Cowley joins us. Hi, Peter.
Hello. Hi there, Tom.
To start with, what kind of things can these virtual assistants do?
Yeah, a little bit of background. So historically, these devices where you could talk to and the reply have been around for about 25 years on PCs. They moved on to smartphones about 6-7 years ago on a variety of smartphones. Voice activation cars have actually been around about 10 years as well, but conversation, or the ability to talk to the cars, just started. So sort of things you can do, you can ask it facts, you can switch on music, video, you can do some shopping, you can control your home, you can add entries into your calendar, etc. Lots of things, yeah.
You've brought one with you along to the studio, so we're actually going to test this out. I'll leave it over to you.
Yes, Tom. So we spent a bit of time before the show just trying to work out what to ask it. So let's just try a few things. So first of all, we'll say, Alexa, who discovered gravity?
Gravity is a discovery by Isaac Newton.
Nice.
Yes. Another one. Alexa, how many kilometres are there in a light year?
1 light year equals 9,460,700,000,000 kilometres.
And just one final one. When I won't try the long one, it'll work out the factorial of numbers. And if I put down 200, we'll be here all evening. So let's have a smaller number. Alexa, 12 factorial.
479,001,600.
I like the choice of maths questions, considering we're doing a maths program. How did these things actually work then?
Yeah, this is complicated. I mean, the biggest thing of all, first of all, is speech recognition. I mean, there are 6,000 or 7,000 languages. There are 40-odd thousand dialects. These things basically only work with a very few languages. In fact, on one of the products from one of the tech companies, it's only just moved away from English to German. So it's speech recognition, and the recognition will depend on how big the vocabulary. So if you've got a vocabulary of 10 words, say 0 to 10, it's probably right every time. But it gets up to, the English language, say, is 70, 80,000. It's probably only right overall about 60% of the time. So it's the speech recognition. Then on top of that, it needs to answer. And so it needs to understand what you're saying. So it's not just the individual words, it's together. And of course, until conversation comes in, it can't re-ask the question another way, which is the way that we're communicating at the moment, isn't it?
Yeah.
So you've got that, the speech recognition, etc. And then, of course, it needs an internet connection. It needs to go off into the cloud to work out what the answer is.
And what about the way it links in with data? So I've heard an example of, if I had told my personal assistant that I need milk, it would pop up and tell me when I went to a supermarket.
I haven't heard that, but yeah, we are moving to that geolocating advertising will hit our phones before long. So as we're walking along, we'll be reminded to pop into that pizza place because they've got discounts on. The bigger issue, of course, is privacy, and people are worried about that. So they say, and I'm pretty confident it's true because I've tried it, because if you disconnect from the internet, it will wake up, but it won't know anything. So it's recognising the wake word, but once it's actually woken up, it's then connecting to the internet. And you've then got to trust, in the way that we're trusting with our phones, about the amount of data floating around, our location, everything else. You've got to trust the system for not misusing that data.
Should we be worried about this sort of privacy angle, the fact that these things seem to know so much about us?
Personally not. I mean, it depends. If you're really worried about that, then don't have a smartphone. Don't go and live in an encampment in Papua New Guinea or something. It comes down to trust. It comes down to governmental trust and big tech company trust about that. Now, as we've heard before, we had a program on Naked Scientist about Apple not releasing data about a phone that were involved as a crime. These tech companies are very keen not to be seen to be leaking data out or giving data to security services.
And what about the future? As I sort of mentioned in the queue, will we be spending all of our time just talking to our gadgets?
First of all, we've got to have conversation. Now, conversation, as I say, is talking. And there is a Cambridge company, actually, was sold to Apple a couple of years ago, called Vocal IQ, which is part of it. So until you can actually converse with it, chatbots they're called, then we're not getting anywhere. But that will be around quite soon. And then you can be using, I mean, the elderly might use it for company. They might used it for teaching children, and then we'll start to use it more than we do at the moment, and to the point really where we might stop using our fingers on smartphone screens, and we will talk to the device and it will respond to us. And a bit like, you're far too young, but HAL on 2001: A Space Odyssey is a good example, and that goes back to 1969, that film.
Yeah, definitely far too young for that one. Thank you very much there. That's Peter Cowley.
And now it's time for our regular myth conception. This week, Katie Haler has been probing one old adage about cats.
If you're a cat owner, you'll know just how much they like milk. They are known to love the stuff, hence looking like the cat that's got the cream when you're pleased about something. My childhood Moggy adored milk. And after all, what's nicer as a cat owner than seeing your feline friend in such a happy mood when that saucer is lowered to the floor? Let's start at the adorable, fuzzy beginning. Kittens drink their mother's milk from birth until they're weaned at about 4 weeks of age. From then on, contrary to what you see in cartoons and movies, milk should be pretty much off the menu. Some cats may be okay with milk, we're talking cow's milk here, but for others it can cause bloating, gassiness and a lot of diarrhoea. So what's going on? Beyond infancy, most cats start producing less and less of the enzyme lactase, which breaks down lactose, the sugar in milk. Without adequate lactase, the lactose just sits around in the digestive system where it ferments. This is what causes the nasty symptoms. This is actually quite common in adult mammals. They don't drink milk beyond infancy, so they don't have much need for the lactase enzyme. In fact, humans are actually the weird ones in this whole thing, as many of us drink milk throughout our adult lives. So, Just like humans who are lactose intolerant, giving an adult cat milk can lead to stomach upsets. Not all cats are lactose intolerant, though. Some keep making lactase into adulthood, particularly if they've been fed milk continuously since weaning, and so their bodies have continued to produce lactase, and they can tolerate milk. But as milk has a high fat content, even cats who can tolerate lactose should only be treated to it occasionally, as it can lead to weight gain. Now, this is all very well, but will it stop your moggy predating the milk bottle? In my experience, no. But if milk actively makes most cats ill, why do they love it so much? The saying, the cat that's got the cream, may in fact hold the clue. If we think about cat ancestry, the ideal diet would have been one that's high in fat. In fact, fat makes food more palatable for cats. So it might not be clever, but they'll probably chance it in terms of having some milk if it's on offer. So the message for cat owners is, take milk off the menu. Or if you can't bear the feline fallout, there are plenty of lactose-free cat milks out there on the market. Just remember that these shouldn't be given too frequently, and however fussy your darling kitty is, there's nothing wrong with a saucer of water.
Katie Haler there. And if you've come across some suspicious-sounding science you'd like us to investigate, do get in touch. You can email chris@thenakedscientist.com, or you can find us on Facebook.
Every 5 years, 2 of Jupiter's largest moons align so that Europa crosses in front of Io. Because Europa is slightly smaller than Io, it's able to block out large amounts of light, which makes it easier for scientists to take photos of this volcanic moon and its features. There are hundreds of volcanic craters, called Paterae, on Io, but one in particular is pretty hard to miss. Loki Patera, named after the Norse god, is an enormous lava lake, and researchers at UCLA Berkeley seize this rare opportunity to capture images of this mysterious molten feature. Izzy Clark spoke to astrobiologist Catherine DeClaire to find out more.
It's, in fact, the most volcanically active object anywhere in the solar system, even more so than Earth itself. It has some very dramatic and enormous volcanoes, and the one that we were focused on in this study was Loki Patera, which is a massive volcanic feature on Io.
I mean, we have lava on Earth, and did these volcanoes have that same lava? Is it all the same thing, effectively?
Well, that's a good question, and it's one that we don't necessarily know the answer to. It's at least similar in composition to lava on Earth, but possibly different, possibly a more exotic, higher temperature composition of magma. We're actually not sure.
And looking at that, what did you find exactly?
Within Loki Patera, this massive lava lake, we saw a fairly smooth distribution of temperatures. There had been some waves of magma that were resurfacing the Patera that started at different points, moved in opposite directions around the volcano, and then converged in the southeast corner.
Gosh, so that's a wave you would not want to go surfing on. But
Absolutely.
Do you know what's causing that wave?
Well, we don't know for sure, but there are some good hypotheses out there that this wave may represent basically an overturned front on the crust that's on the surface of this lava lake. So we have crust that over time becomes cool and thick and eventually unstable, and it sinks down back into the lava lake when it becomes unstable. And so we have this wave of sinking that then propagates all the way across the Patera.
Now, Io is one of Jupiter's moons. I mean, this is really far away. How are you even able to measure this and find this out?
That's a great question, because from direct telescope observations, we're really not able to get this level of spatial resolution at all. We were able to get this kind of resolution when Europa, another of Jupiter's satellites, was moving across Io. So we have Europa passing in front of Io from the point of view of Earth, and it systematically blocked light from Loki Patera. And by looking at how the emission from Loki decreased as Europa slowly moved across it, we could reconstruct the distribution of emission from within.
And what is so important about Europa crossing Io that has made this possible?
Europa crossing Io is a fairly rare occurrence. This only happens once every 6 years when the orbital geometry of Jupiter's satellites lines up just right from the perspective of Earth so that we actually see these satellites cross one another. But something else that makes it possible to get out the intensities of these volcanoes is that while Io is very bright, Europa is almost completely dark at the infrared wavelengths that we observed at, because Europa is covered in water ice, which absorbs all of the sunlight that's incident on it. So it's almost invisible.
How precise can we get in terms of imaging this effect?
So Loki Patera covers a total area of 20,000 square kilometers. So it's about the size of the state of Massachusetts or of Wales. The image we reconstructed has a resolution of somewhere around 10 kilometers, maybe a little bit better than that. And so you're talking about a resolution of 10 kilometers across all of Wales or all of Massachusetts.
Gosh, that's quite high detail.
Yes.
Why is this study important?
So in general, what we'd like to do is construct a very generalized understanding of how volcanic activity works, not just on Earth, but everywhere in the solar system. We'd like to know in different environments, how does geological activity differ, and how Earth and Io are different from one another, and then we can start to speculate about the full range of styles of geological activity that might be present throughout our solar system as well as elsewhere in the galaxy.
Catherine Declare, and that work was published in Nature.
You're listening to The Naked Scientist with me, Georgia Mills, and with Tom Crawford.
Now for my favourite subject, maths. We're going to be investigating how maths earned the title of the language of the universe, finding out how it crops up everywhere in daily life, and asking if aliens would really understand it if they came to Earth.
But before that, let's meet the apparent mathematicians of nature, the bee. They, of course, build those fantastic hexagonal honeycombs, but apparently they're also able to count. And Srini Srinivasan from the University of Queensland joins us now to tell us more. Hi, Srini.
Hi, Georgia. Thank you for having me on your show.
No problem at all. So tell me, how did you work out whether bees could count?
Well, we trained them to fly down a tunnel, a small corridor that carried a reward of sugar water at the far end. And we had a series of landmarks, identical landmarks, that they flew past along the way. And only one of the landmarks carried a food reward, sugar solution. And they had to, by flying through and testing out the various landmarks, they had to work out which particular landmark carried the food reward, whether the second one or the third one or the fourth one or the fifth one and so on. And we did find that, for example, with some training, they could tell which particular landmark carried the food reward.
I'm assuming these landmarks were identical apart from the number of them the bees had flown past.
Exactly. And then you've also got to make sure they're not cheating and using another cue that they potentially could also use as honeybees. They have a lovely odometer, a visually driven odometer that tells them how far they've flown by measuring how much the image of the world has moved past their eyes. And so they could be using that as a cue. They could be measuring distance to the correct landmark rather than counting these landmarks, right? So the way to control for that is to actually randomly vary the separation between the various landmarks to make sure that they realize that distance is not a useful cue and they really have to learn how to count.
So how high can bees count?
Well, it looks like they can manage up to 4 in this sequential counting task, not much more than that. But surprisingly, 4? that number 4 seems to be a fairly almost universal number among many animals, and also among children, for example. We can count only up to 4 or 5 when the numbers of objects are actually briefly flashed to us, presented to us on the screen in a very temporary way. It's called subitizing, I believe. That's the name for it. And it's a form of primitive counting that we indulge in, or we have to sort of cope with when we have limited processing time. And animals seem to have that, and so do infants. So it's a kind of a basic counting module that all living creatures seem to have, more or less.
Oh, right. So why is it useful for bees to be able to count to 4?
If there are prominent landmarks along the way, it does make sense, I suppose, to keep track of them as well as the distance traveled. So that could aid you in locating, pinpointing your source. Also, if a bee needs to decide whether it's worthwhile landing on a flower or not, if there's a large number of bees already there, it's probably not worthwhile for it to actually get down there and try to, jostle amongst these various bees and spend time and energy trying to get to the food source. It might as well, try a different flower. So it does help for bees to be able to have a rough idea of how many bees there are on a particular site.
And they just don't need to count above this number then?
It seems like anything beyond 4 it translates to many, and they cannot really distinguish between 4 and 5 and 5 and 6 and so on.
1, 2, 3, 4, many. It would have made maths classes a lot easier. So are bees particularly good at maths then? Are there other animals that can count too?
Counting has been, it's been looked at in fish, in birds, in chimpanzees and so on. And this magic number of between 5 and 6 seems to crop up in almost all the species. So it's actually quite interesting. So birds, for example, probably need to know how many eggs there are in the nest and whether one of them has fallen off or been taken away by another bird. Quite often, counting a number of animals in a pack is probably helpful if you're a wolf or something, when you decide whether you want to go to a fight with that pack or not. So that sort of counting ability seems to be there amongst a lot of animals, not just bees. And I wouldn't claim that bees are the best counters in the world.
And so finally, I mean, it's really cool that bees can count, especially as they've got very, very small brains. But why are you studying this?
It was by accident. This is not the main focus of our research, I should admit. This was just a one-off thing we did. We were using this tunnel paradigm to study a whole bunch of other things that bees do. For example, the fact that bees measure, that they're excellent navigators, and they measure how far they've flown, not by measuring, the time of flight or the energy consumed or counting a number of wing beats that it takes to get to the food source. They actually do it visually by measuring how much the image of the world is moved in their eyes. And that's something we were able to do using this tunnel paradigm, by making bees fly down this tunnel and looking to see how they danced when they came back, because the dance conveys information to the other bees about how far away the food source is.
Ah, yes, this is the famous waggle dance, isn't it?
The waggle dance, exactly right. And so when they fly in this narrow tunnel, even when they fly a short distance, they get comprehensively fooled, and they think they've flown a very long distance because they experience a large amount of image motion on the way to the food, because the walls are very close to the eyes, and as is the floor. So even a small amount of forward movement makes you think you've flown a long distance.
So bees are just all-round clever clogs then. Thank you so much. That's Srini Srinivasan from the University of Queensland.
That's maths in the animal kingdom. But what about in the human world? A lot of our decisions, although we may not realise it, rely on maths. Game theory is the study of mathematical models of conflict and cooperation between intelligent, rational decision makers. It can be applied to almost any subject, including economics, political science, psychology, even biology. The last one is of particular interest to Sergei Gavrilets, a mathematician at the University of Tennessee, who uses game theory to model early human behavior.
In our models, we included 2 different types of games. One is coming under the name of us versus nature games. And you can think of a situation where group members have to go on a hunting trip. Or you can think of a situation where they have to clear part of the forest to be able to plant some plants there. And the other type of games is us versus them games. And that would be a conflict with a neighboring group over, say, territory, or over some mating opportunities.
So would I be right in thinking the idea of us versus nature, say there are 8 people in your group and you need to hunt a mammoth for food, sort of thinking like old hunter-gatherer style. So say, provided 4 people turned up, we would kill that mammoth. But then the idea is that only means half of the group need to give effort for the whole group, because the whole group will be fed, for the whole group to get the reward. Is that the kind of game theory thing where people are thinking, should I commit and put the effort in, or can I be lazy and sort of free ride through it? Is that kind of the idea here?
Yeah, exactly. That's the idea. Perhaps we would need more than 4 people to kill the mammoth, maybe like 10, but indeed, that's the idea. This type of games also is coming under the rubric of the volunteer's dilemma. Right? Just imagine a situation like you and your family are watching a movie, and then there is a phone call, all right? And the phone is in the next room, and you don't want to go there, but it's so annoying. So this is a situation where everybody would benefit from somebody going and answering it, but nobody wants to do it. So this is a typical volunteer's dilemma.
That ringing phone example occurs pretty much daily at my house. That was Sergei Gavrilets there from the University of Tennessee.
And now that we have a better grasp of what game theory is, Tom, I understand we're going to do a little experiment of our own in the studio.
Indeed we are, Georgia. It's called the Prisoner's Dilemma. And obviously, as our resident mathematician, I'm going to be running the show with yourself and Peter Cowley, who's still with us, our willing volunteers.
So how does this work?
Right. This is a hypothetical scenario where both of you have been caught committing a crime.
Oh, no. What did we do?
Say you've robbed somebody.
Okay.
You've done a bit of pickpocketing. And you've been caught by the police, and the police say to you, right, we have enough evidence to put you in jail for 1 year. And they say this to both of you, but you're separate and you can't communicate. And then they also say to you, if you sort of snitch on your friend and cooperate with us, then we'll let you go free and your friend will go to prison for 7 years. So you're both given these two options. You can either cooperate with the police, which means you go free and your friend gets 7 years in prison. You can just say absolutely nothing and get 1 year in prison. And what will happen if you both cooperate? Then, of course, the police are like, oh, well, you're both just making this up if you're both blaming the other person. So you'll each get 3 years if that happens. So I'd like you to both write down whether you would cooperate with the police and snitch or stay completely silent. Of course, you're not allowed to communicate here. You can't discuss with each other what's going on.
I want Peter to come back on the show. So I'd want to be nice. Okay.
Hypothetical. Bear that in mind.
Well,
okay, right.
Yeah, we're sitting far enough apart we can't see each other. So we can see each other, but not our bits of paper. I've written something down.
I've written something down too.
So are we supposed to show it up like a game at Christmas?
Well, I'll tell you what. I will. So, of course, we can do the maths here and work out what's best. So if we do this first, then we can see how you both thought about this problem. Let's start with Georgia. Let's assume that Georgia has decided to cooperate with the police. So from Peter's point of view, Georgia has cooperated and snitched. So at the moment, if Peter stays silent, he is getting 7 years in jail because Georgia snitched. But if Peter cooperates with the police as well, his 7 years goes down to 3. So if Georgia snitched, Peter should also snitch. But if Georgia stayed silent, then that means that at the moment Peter has 1 year. But if he snitches, he goes down from 1 to 0. Whereas if he cooperates, he goes up to 3. Yeah. So if you think about it from an individual point of view, you're always reducing your jail time by snitching, by cooperating with the police. But if you think about it from a team perspective and you add up the total number of years in jail, the best option is for you both to stay silent. Because if you both stay silent, you get 1 year each, a total of 2 years. Whereas if you both snitch, which is what you should do to maximise your own personal benefit here, your total time in jail is actually 6 years. And so this is basically how game theory works in a nutshell. It's considering the individual benefit and individual decision as opposed to the team benefit and the team decision. So let's see what you actually have said. So Peter has decided to stay silent.
No, I'm sorry, I snitched.
So I end up in...
So Peter is clearly far too nice. And
please come back on the show. I'm sorry.
So the final result of that is how many years?
The final result would be Georgia would go free, and unfortunately, Peter, you would be in jail for 7 years.
See, I'm a team player.
I'm really
Georgia,
sorry, Peter.
what are you?
I just can't. I can't go to prison, man.
But as we said, this is game theory. It's the team dynamic versus the individual benefit.
So how do we use this? Who was right, essentially? I mean, I've betrayed Peter massively, but how do we use this if I'm ever in this situation? Should I be using game theory in this way?
It's not so much that you can use it to inform your decision making. It's perhaps just being aware of what's going on. And it's a way of modelling how we make decisions as rational decision makers.
I see. So it's you look at what you've done, and this is a way to understand why. I know in nature, game theory is used all the time to explain why animals do certain things the way they do. So I guess it's a really useful tool in that way.
Exactly. It's just the idea of thinking things on an individual level and on a team level. There are different options there.
Well, thank you, Tom, for showing us the delights of game theory then. And thank you, Peter, and I'm very sorry I've put you in prison for 7 years.
You're listening to The Naked Scientists with me, Tom Crawford, and with Georgia Mills.
So we've just heard how maths can be used to explain our decisions, but can it be used to influence them? Well, maths could be making waves in the world of advertising, because using clever mathematical techniques called genetic algorithms, scientists are able to create self-evolving adverts inspired by Charles Darwin's theory of evolution. Visa Sharbi works on genetic algorithms at Brain Labs and joins us now. Hi, Visa.
Hi, Georgia. How are you doing?
I'm very well, thanks. Thanks for joining us. So what is a genetic algorithm and how do they work?
So genetic algorithms are a technique used to solve these really difficult mathematical problems called optimization problems. Within optimization problems, you usually have a lot of parameters that you need to vary, and it's not immediately obvious how to vary those parameters to get you to your optimal solution or your sweet spot. So genetic algorithms are ways of kind of a really efficient way of getting to the best solution possible. The naive way of solving them would be, of course, to just try out every different possible set of variables until you find the set which works. And genetic algorithms just completely skip that and taking a cue from evolution.
So how does evolution come into it?
The way evolution typically works is that within species you have variation, and that variation lends to different members of that species being more successful. And the more successful an animal is, the more likely it is to pass on its genes, kind of propagating those kind of good genes that allow it to be successful. And we kind of take that and use that as inspiration for the genetic algorithms by using it to come up randomly with solutions for how to essentially pick all the different parameters in our huge optimization problem. So once we randomly pick different solutions, we see which ones are the best, and then by ranking all the best ones, we get to take all the best features from the ones at the top of our ranking, and those then get passed on. By taking all the best bits from all the different solutions that we get hopefully what is kind of the best solution overall.
I see. So in evolution in the wild, for example, a rabbit might have 10 rabbit babies. I've forgotten the name for a rabbit baby. Maybe the one that's the fastest at running or the biggest will be the one that goes on to survive. It will have 10 children. The best of that will survive. It will go on, so on and so on, so on, until you get the ultimate rabbit, I suppose.
The ultimate rabbit for its environment, yeah, exactly.
And this is what you want to do. You want to take this out of evolution and apply it to other things.
Exactly, yeah. Apply it to kind of various problems where there is kind of one way to be best suited for some environment.
In evolution, there's this natural variation, but there's also DNA mutates. This is when there's an error in the code and it changes. So do you incorporate this into your model?
Yeah, exactly right. So we do introduce random mutations into our solutions. So once we've generated a random solution and that's turned out to be the best, for successive generations, we'll enter random mutations to kind of try and mix things up a bit. The reason we do this is to kind of, the technical term is to kick you out of your local maximum. And a nice way to think about this is if you're trying to find the peak in a mountain range and you ended up on kind of a smaller mountaintop, by introducing mutations, we might kick you out of that smaller mountaintop and try and get you onto the highest peak.
I see. So for example, if you didn't do the mutations, you might get stuck in this little zone and any deviations will send you downwards. They'll be worse. But if you introduce this way of sort of more random things happening, you can get something totally different, which might be even better.
Absolutely. It's kind of exploring and seeing if there's something better out there. Exactly right.
Okay, so could you give me an example of how this could be used in practice?
Cool. So a really cool example of how it was actually used in real life was there was a coffee company which had an advert up on Oxford Street. They had lots of different images as well as lots of different bits of text, and they would combine these to make different adverts. And then they would show these adverts on a bus stop, one of those kind of bus stop ads in Oxford Street. And then by looking and registering at how long people would stare at those ads, they would determine if the ad was successful or not. Once they've got enough data on how successful certain ads have been, they would take features from the most successful ones and mash them together to try and make even more successful ads, and they would repeat that process.
I see. So something like how big the text size is, the colour, the image, the words used, all of that put together, and it just sort of keeps going until it has the ultimate ad.
So one of the things that they found worked really well were pictures of hearts, but what they did find, I think, is that the text that it came up with was fairly nonsensical. And that may have been the reason for people staring for a lot longer.
I was going to ask, because I often stare at ads that make me angry. Could this not be leading us down the wrong path?
I think there's still a lot of refinement to go in the area of auto-generated ads. But like they say in advertising, if it's gotten you talking about it, it's done the job.
I suppose so. And so is this where advertising is headed?
It'll be interesting to see where it goes. I mean, certainly there's a lot more data now available in order to come up with things like auto-generated ads, but it'll be interesting to see whether it's actually something that takes off in the real world.
I gotta say, my dad's a copywriter. You're going to be putting him out of business here.
I think you'll have a job for a long time to come if you were able to actually see the ads that the genetic algorithm produced. But it's certainly exciting.
And are there any other applications this kind of thing could be used for?
Absolutely. So outside of the world of advertising, I know Unilever designed one of their nozzles using a genetic algorithm, and then just within other areas of advertising, we use it at Brain Labs all the time in order to come up with solutions to big mathematical problems that we've got.
I guess it made sense copying what nature has been doing for millions of years. It's worked pretty well so far.
I think humans are doing okay. So yeah, it's working pretty well.
Wonderful. Thank you so much. That's Fusar Shabi from Brain Labs.
So far, we've met the mathematicians of nature and also seen how mathematical modelling can explain and even influence human behaviour, which leaves just one question left unanswered. If maths really is the language of the universe, would aliens understand it? Professor Ian Stewart from the University of Warwick.
It's a more difficult question than most people tend to think, because we've been brought up with this idea of maths as the kind of universal truth. It's somehow truer than anything else because it's all perfectly logical and it follows from basic principles and so forth. And 2 + 2 has to be equal to 4 once you've decided what 2, 4 plus and equals mean, and there's no real way around that. And all of that's very true. So I doubt you'd find aliens who don't think that 2 + 2 = 4, but you might find aliens who don't really understand 2 or plus or equals. In fact, Henri Poincaré, who was one of the great French mathematicians at the end of the 19th century, beginning of the 20th century, said, in the real world, equals does not behave the way we think it does. In mathematics, if A = B and B = C, then A = C. In the real world, if we think A = C, actually they might be very slightly different, but we can't measure the difference. I suppose you could only measure things to within 1 centimetre. If two things are 3/4 of a centimetre apart, you think they're in the same place. And if the second one is 3/4 of a centimetre away from one of those, you think that's in the same place as the other one. But then the two of them could be 1.5 centimetres apart from each other, and you could tell they're different. So in the real world, if A = B and B = C, then maybe A is different from C. And this is what Poincaré said. So mathematics is an idealisation of what's out there. And I think that different creatures from different environments with different ways of living, different concerns as to what's important, might set things up in a different way.
It almost sounds to me like you're saying that the maths we have on Earth has evolved from our environment on Earth. And so the maths that aliens use would have evolved from their environment.
I think the more, if you actually start thinking about it, what we consider to be absolutely fundamental mathematical concepts are very closely related to the kind of creatures we are, the kind of world we live in, and how we perceive that world. Our counting came from keeping track of discrete objects or events. If I've got a lot of sheep, I'm a farmer with a lot of sheep, say 15 sheep, it's useful to know that I've got 15 sheep. I've got to be able to count up to 15. If one of them's missing, I will spot it. If you just say, well, I've got some sheep, it's not too many, it's not too few, you lose one of your sheep, you don't realise it's gone, and a bit later you lose another sheep and still don't realise it's gone, and suddenly you're down to 2 or 3 sheep and you think, something happened there. But most of it happened so long ago you can't do anything about it. So we count things, and counting the number of days in a month in the cycle of the phases of the moon, that was very important to a lot of early civilizations. So the idea of going 1, 2, 3, 4 and so on is very basic to us. But creatures that lived in a completely different environment where there aren't any discrete objects, I'm thinking of maybe creatures that float around in the atmosphere of a gas giant planet. They're more like giant amoebas or something. They flow, everything flows. And so you try to explain Pythagoras' theorem to one of these creatures and say, well, take a triangle with corners at A, B, C, and it sort of puts down A, and then you say, now mark another point B, and it says, okay, I've got point B, but A's disappeared. It's gone off on the blown away on the gas, on the wind. There aren't any rigid triangles. And they might have real trouble with concepts like triangle. On the other hand, turbulent vortex flow is something they would think is absolutely trivial and straightforward, a child of whatever would understand. And we have really, really serious mathematical problems with it.
It sounds to me like maths is still maybe our best bet with communicating with it. I mean, better than like language or our culture, surely, in terms of what they might have a chance of understanding.
I think that's probably right. I think to be to be a bit less imaginative about the possibilities and just say what's actually likely. Maths has a kind of universality that communicating with them with language would be difficult. They don't speak the language. They might not even hear sounds. Poetry probably isn't a great idea. The works of Shakespeare would not particularly impress them. Music possibly, but think of listening to music from other human cultures. It's very hard to get used to, and no generation of parents understands the music that their kids like. Teenagers are aliens. It's fairly notorious that musical tastes are very different. If there are points of contact, it's somewhere you can start from. So, very likely aliens would not use base 10 numbers. They might use some sort of number base because it's quite a neat idea for encoding numbers. But, we've got 10 fingers and if you count thumbs, and that's probably where base 10 comes from. There's nothing special about 10. So an alien with 7 tentacles might work in base 7. Yeah. But they would rapidly think, oh, these guys are working in base 1-3. That's 1-7 plus 3. We call it 10. They call it 13. And we would rapidly say, oh, they're working in base 7. And, you can translate from one to the other very straightforwardly. So differences in notation, differences in number base, differences in, we think triangles are basic. No, they prefer rectangles, whatever. That wouldn't be a barrier to communication. It would be something to puzzle out. And if we're on that level, there would be this great possibility that the aliens know some maths that we don't. And we know some that they don't. And I'll trade you the proof of Fermat's last theorem if you can tell me how to prove the Riemann hypothesis. You could actually have interstellar trade in mathematical theorems.
Being a mathematician, I absolutely love the idea of interstellar trade in maths. That was Professor Ian Stewart. And thanks to our other guests this week, Visar Sharbi, Sergei Gavrilets, Srini Srinivasan and Peter Cowley.
And finally, it's time for Question of the Week. And Izzy Clark has been concentrating on Kevin's tiring topic.
When we exercise our bodies, we get tired and have to stop after a bit. Eventually, we get fitter and more endurant at those tasks. I know we can suffer fatigue in certain mental faculties too. Decision fatigue springs to mind. If we perform difficult mental tasks, does our endurance at those tasks improve over time, or are we doomed to make poor decisions in the afternoon forever?
We're all familiar with that post-lunch afternoon fatigue. You can't make decisions and everything takes a bit longer. But can we train our brain to improve at tiring tasks? Duncan Astle from Cambridge University has been thinking it over.
Just as with physical activity, difficult mental activities show big practice effects. That is, the more you do them, the better you get. And carefully controlled studies have shown that practicing difficult mental activities, like remembering all of the objects within a picture, can make you much better at those tasks. And this improvement can be mirrored by changes in the brain. For example, the brain areas involved in attention and memory can become more strongly connected by this kind of practice.
Just like with physical exercise, mental practice can improve our skills. But if I go for a run, I will definitely need a rest to stop and catch my breath. Does this apply to our brains as well?
Even where we can improve at something by practicing it, this doesn't mean that we no longer require breaks. Demanding cognitive activities can be tiring. Forcing yourself to continue is unlikely to be optimal, and regular breaks are necessary when performing demanding tasks, even when we're highly practiced.
In that case, I'll go pop the kettle on. And if you're taking any exams at the moment, you should probably do the same.
We know that when revising, it's really important to space revision out. frequent bursts of revision are much more effective than the same amount of revision in one long block. This is sometimes called the spaced practice effect. This is because each time you revisit information, you strengthen the corresponding memory traces. So the more times you actively retrieve the information afresh, the more durable those memories become.
So after all this training, can our brain automatically adapt to take on any task?
Whether these benefits will transfer to other mental activities that we haven't practiced is highly controversial, and there isn't much compelling evidence for these generalised benefits of mental practice.
Oh, right. Maybe not then. Thanks, Duncan. Next time, we're turning up the heat on Jim's question.
I recently started to attend a hot yoga class where they claim that the 40 degrees Celsius room helps warm up your muscles faster. Knowing that the body tries really hard to maintain a very narrow temperature range, I was wondering if the muscles are really getting warmer, or is there something else going on? What happens at a cellular level that makes it better to have a warmed up muscle?
If you think you know the answer, you can email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join in the debate on the forum, thenakedscientist.com/forum.
And that just about wraps us up for this week. This programme was put together by Tom. And if you liked this, be sure to check out our new video series, Naked Maths, presented and produced by Tom, coming later this month. Next week, we'll be back with a Q&A special, so do send in your questions to chris@thenakedscientist.com. The Naked Scientist comes to you from Cambridge University, and it's supported by the STFC, the EPSRC and Rolls-Royce. I'm Georgia Mills, and thank you very much for listening. Goodbye.